Alright, hell yeah. So we have part 4, the moment you've been waiting for. We're going to do some differentiation, and yeah, we're finally doing it. So this is what we're going to go over. Let's just talk about the problem real fast. We have this disk, it's rotating around a pivot. Hell yeah, it's kind of wonky, you know what I mean? So we went over that in parts 1 and 2, and so, and we calculated, we already got the answer in part 3, just from geometry. So we're going to take a look at that. So when this angle goes to 60, kind of way out here, sure, this actuator, I think they call it a follower, is down here. Cool. We don't really care about that. What we do care about is what's its velocity. That's what we want to know. We want to know the velocity of this follower. So how do we do that? Well, I showed that we could just figure out what its location was, and then instead of going and then proceed forward to 61 degrees, cool, and then see how far that distance moved just using geometry. And if you know how long it took to go from 60 to 61 degrees, booyah, now you have a distance divided by time. Okay, hell yeah. So now how does the differentiation process work? I'm going to try to go through this as fast as possible, but then we're going to go back and maybe slow down. So we still use geometry, and this is really important because you still have to kind of link. Well, you have to find the thing that actually makes sense, and it's this length right here. In the other video, I called this just y. You know what I mean? So this is y might be the distance from this origin to the actuator. Cool. And so then we're just going to bring this out to and in our problem, let's see. In our problem, I didn't draw this angle in. My bad. But this is the angle that gets swept out. So these pictures are similar. I just swept it out more. And then here's our eccentricity. So here is our point O. This is our pivot point now. And the tallest point could have been on the vertical. So it's just kind of good to kind of see what a problem looks like. But then we swept it out. Now this is only 45 degrees. We would actually sweep it out farther. This point A would be a little bit lower. Okay, the main strategy is, what is the strategy? Well, it says calculate the velocity of the follower. Sometimes it says, hey, calculate the velocity of the follower A as a function of theta. So then it kind of helps you and spells it out. We're not trying to find the velocity as a function of time. And so just think about those two things for a second. So what we need, or what we decided that what we can do to find the velocity is to figure out what this height is. If we know that this height or this distance, if we know what that height is at any given angle, well, hell yeah. Then we're kind of in business. Then it's not too big of a leap to see that, hey, so let's just pretend like we already found these, because we found these in part 3. So y is just this plus this. And guess what? It's a function of theta. Everything else is totally known. We know the radius, we know this eccentricity, and so booyah. So that's going to be y. And I should have wrote this in here instead of putting the derivative already. So we have y is equal to those two things. And sweet. So now what we're going to say is well, I want to change y. I want to do a derivative of, I want to change y and change time at the same time. Now what we did, let me spell it out. We took y, we had an equation for y as a function of theta. And then what we did is we changed the angle. Cool. So then we found the change in y. And then we also, so we got that, checkbox. But we also found out that we changed our angle. So we changed our angle, let's say we went from 60 degrees to 61 degrees. In part 3, we went from 60 to 60.001 degrees because we knew what the hell we were doing. And we just wanted to make that increment very, very small. So, but then how the hell did we actually find the velocity? How did we find the change in y, change in time? Well, then we went from, okay, we knew the change in the angle, but then we had to know how much the angle is changing. So then we come back up here, and then we get this, this is angular speed. This is going to be in radians per second. It's in revolutions per minute, but we change it to radians per second. Now the symbols for this are theta dot. This is going to be d theta dt. So omega is the same thing as theta dot d theta dt. Change in theta, change in time. Okay, hell yeah. So we knew that. So we have this change in angle. So sometimes you're just like, oh, it is the equation. And then this is going to be, so we have some number as a change in angle, change in time. So these two things we know. We know the number for the change in angle. That's going to be a change in angle of 0.001 from part 3 degrees. Let's pretend like we knew that number in radians. And so we know this number. We know, and then we know this. Well, hell yeah. So then you can actually get the change in time. And so that's how we did that. So then we know the change in y, and then we know the change in time. And I think this actually, yeah, it's so bizarre how I kind of know these things from this intuitive level. Okay, hell yeah. So, but yeah, this is what we did. We took this change in angle, and then what did we do to it? We divided it by the change in angle per change in time. We did that in part 3 if you want to go back. So it's like, this is how I can definitely learn. It's like, hey, use the numbers to where they're logical and you know how to use them. But then go back and see what you did to the numbers. So hell yeah, the change in angle canceled, change in time pops to the top, and then you have change in time. But this is synonymous. What we did right here is synonymous to the chain rule. Because we want to find that we know the change in y. We figured that out using the geometry from part 3. But we want to know change in y, change in time. We didn't know that, but we did know change in y, and then we knew the change in the angle. So if we stack them like this, it's just like, well, we never did that, right? We never took the change in y and then just divided it by the change in angle. But check this out, because we did. Because now you have the change in angle, change in time. And that was that omega. And is that what we did to it? We got this change in time component. So if you look at this whole thing, because these cancel, is change in time. But it's 1 divided by change in time. So, damn it. All right, now this is cool. So let's put this aside and go back to kind of what we know. I had to take like 1 step forward and then kind of 2 steps back. So we found the change in time. We put that off to the side. That's going to be that part. Come back to that later. Then we know the change in the angle, and we have to take that and then divide it by the omega. Cool. So we're going to have, so hell yeah. So you're going to have d theta divided by d theta change in time. So this is what we did to it. This is taking that change in angle that we did, then dividing it by the angular speed, which is the same thing as finding that change in angle, and then multiplying it by 1 divided by the radians per second. Okay, so and that was going to be our change in time. All right, hell yeah. Then once we found the change in time, then we had to divide it by the change in y. You know what I mean? So we found 2 separate things. We found the change in y, we found the change in time. Take this divided by that gives you the velocity. So now the only thing in the chain rule is just it's kind of inversed. So we have dy, we know what that's going to be, and then we're going to divide it by the change in theta, but then we can multiply that change in theta by the angular speed, and that's going to give us that change in time downstairs, compared to just finding the change in angle and then dividing by omega. You know, if I'm starting with this upstairs, I got to divide by the angular speed to find change in time, and then I got to put that change in time back downstairs. So the chain rule just does that process, just all in one go, where you're just going to have your change in angle downstairs, and then you're going to multiply it by the change in angle per unit time, which is the angular speed. Holy hell, that was good. I just wanted to go over this fast, but this is the type of stuff I would go over a lot slower. But I think that was a pretty good explanation of why you use the chain rule. So, so let's go back to our equation, because right here we have our equation for y. Y is this plus this, and we want to change it with we want to do a derivative with respect to time. But there is no time. I said there is no t right here. We have a theta. We don't have a t. You know what I mean? We have a theta right there. Again, we don't have a t. All right. Now, this isn't the video to go into it, but how do you replace this with just t? Well, you have to pick some initial angle, whether it's 0, you know what I mean, and then say, hey, we're gonna have a change in angle, change in time. This is kind of the definition of a derivative. Start with a position, and then and then I mess this up all the time. This is not true. The units on this. This would be in radians, and this would be in radians per second. So let me pause. All right, hell yeah. So this is going to be, and we go over this step right here. We make sure to check our units, because if I want to know the angle per unit time, I need an initial angle, and then I need a change in angle, but then I also need a change in time. So what this would look like would be theta initial plus the angular speed times time. And I'm sure you've seen this quite often. This is an unchanging variable. It's just where you started the system. You know what I mean? Typically, 0 will be like horizontal, vertical or horizontal. In this case, theta naught would be 0 degrees. Maybe at time is equal to 0 degrees, and it would be in the horizontal. And then to sweep out to 60, well, you would take the angular speed. We're going in this problem, we're going hella fast. We're going 104 radians per second. To go 60 degrees, that's going to be 1 radian. So in literally 1/100th of a second, you're already at 60 degrees. But there you go. So you would have 0 plus 104 times the time. And so if you wanted to, to do the problem that way, you would have to say, hey, find the velocity of this when time is equal to maybe 1 divided by 104 seconds, 100th of a second. So that's how you would do it with respect to time. But then you just take the derivatives with respect to time. And if you're more used to that, if that just feels comfier, like hell yeah, go for it. You're still going to have sines and cosines, but you're not going to have, once you do the derivative, you're done. You won't have any chain rule-esque functions. But as we'll go through this, everything is the chain rule. You know what I mean? Because you use a process called hey, I'm just gonna see everything underneath this square root. I'm just gonna call it u. You know what I mean? And then just pretend like it's almost just like one simple variable. Okay, hell yeah. And so we're going to go over that process. But I think it's going to be a lot simpler to do, to why we do. So right here, all I see is thetas. So when I go differentiation with respect to time, I can't do that. But since I have thetas, that's the only thing that's the only variable that's actually changing in this problem. R doesn't change, E doesn't change. So just always count your constants. Be like, okay, everything else is constant except that variable. Okay, sweet. And then so we're going to take this whole equation and then do that same thing. We're going to differentiate with respect to theta. And again, that's going to be this part of that. This does not give us the angular speed. It gives us kind of this limbo part. You know what I mean? Like it gives us, like, initially in part 3, we found the change in y, cool, and then we knew the change in theta, cool, and we used that to find the change in time. So those 3 components are what we put together. Chain rule is no different. Change in y, change in theta, and then the angular speed. Hell yeah. Okay, so Sure. So just common differentiate, if you're differentiating this, hell, I see a cosine, maybe I know how to turn that into negative sine theta, you know what I mean? Sweet. But one other thing happens, because we have to take the derivative with respect to theta, and then theta, so the chain rule, so if we have dy dt, I always put this y in brackets. That is the function. You know, I mean, we have a function y is like all this stuff theta, all this stuff theta. That's what we have going on. Basically, we have dy of theta dt. And so to do the chain rule, we're going to change that function y of theta, put that in brackets, but we're going to differentiate with respect to theta, which we can do using all our properties. And then the chain rule says d theta dt, and if you cross these out, you know what I mean? Hell yeah, you're just back to that same thing. So that's where, kind of logically and mathematically, it just goes back to what we want. All right, hell yeah. So yes, and then this d theta dt, just to save pen strokes, is just theta dot. You know what I mean? And I think it'll be easier long term to kind of see this as a variable. Like, hey, this sometimes is just omega. It's the speed that they're given. Cool. But sometimes this omega is also a function of time or theta. You know, that can also be changing, so keep that in mind. But in our problem, this is just a number. So theta dot for our problem, hell yeah, at least it's just a number. Okay, so cool. So we're going to differentiate this with respect to theta. Like you would just do that as a separate problem, but then just make sure to multiply it by this theta dot. That's the biggest part that you can easily mess up. Okay, so I found out theta dot from the problem statement. It says this thing's spinning at 1,000 revolutions per minute. Here's the factor label. We have revolutions per minute. I need to cancel out minutes with seconds, so I know that 1 minute is 60 seconds. Now I have revolutions per second. These two numbers, 1,000 divided by 60 is 16.6. You know, repeat. So about 17 revolutions every second. Hella fast. Okay, so that's revolutions per second. I need to, what do they say? Convert to radians. So one circle is going to be 2 pi radians. And again, what the hell's a radian? We measure the radius, cut it with a string, drape the string around the circle. We'll go to there for the first one, and definitionally, this angle is 1 radian. Let's keep doing it, and it's about 60 degrees. So you can do it about 3 times, get halfway around, 3 more, and basically get all the way around. But it'll come up just a little short. 1 radian is 57.3 degrees. Sweet. All right, but hell yeah. So if I said this went 16, let's say 17 revolutions per second, and each revolution has 6 radians. See, 1, 2, 3, 4, 5, 6. So 17 times 6, always use the number 6 as just a back check. So I should get like 102 radians per second. Sometimes multiplying by 2 pi just doesn't ring a bell, but that's going to be 6.28 because pi is 3.14. And if you stack these, oh hell yeah, you can easily see. There's the 8, there's the 2, there's the 6. All right, booyah. Okay, so if you do that factor label, we get this number. And again, this is a constant. Anytime you're doing differentiation, like always note your constants. Like in this problem, maybe this is on a motor, electric motor, not too much, difference in torque. So this thing's going to run at a constant speed. You know what I mean? Just like your table saw is going to run at a constant speed, pretty much. Unless you're really bogging it down. Okay, hell yeah. So now we just kind of do the common practice of differentiation. You know what I mean? We use, and a lot of it's like, hey, go back to the basics of like, hey, so if I have an equation y is equal to x squared, all right, what's dy dx? Cool. That's going to be 2x. Cool. Now let's do this one because you need to know it. What's dy dt? Like, I don't know. I don't see a t here. Well, put one there. You know what I mean? Put t to the 0. You know what I mean? You can do that. And so if we do that, we're going to be like, well, maybe you shouldn't do that. Maybe you should. If you did that, well, one of the rules is the product rule. Hey, if I have two things here, I need to do the first times the derivative of the second plus the second times the derivative of the first. So let's do that. You know what I mean? So we're going to take the first, so we got x squared, derivative of the second. We bring down the 0, and then we go t to the negative 1. Okay, and then we're done. And then plus the second, so we're going to have t to the 0 plus the derivative of the first, 2x. Okay, so what's this 0 doing? Okay, that makes that 0. You know what I mean? So whatever funkiness, you know, just by adding this t to the 0, you know, sometimes that could mess with your mind, but it does help. You know what I mean? When you take the derivative with respect to time, you're like, I don't see time there. And then we'll do it one more way. And then t to the 0 is 1. So booyah. Oh, I feel like I messed up. All right, hell yeah. No, I mean you could do it that way, but the first. So the first times the derivative of the second, that's check. But the second, t naught times the derivative of the first, well, you're still taking the derivative with respect to time. You know what I mean? You're still doing this. You're still doing dy dt. You're taking that function. So on this side, you're saying d of this function, t naught, dt. You know what I mean? So you're using the chain rule, but still, once you get to the second times the derivative of the first, you're still taking the derivative of x squared with respect to time, and you don't have a time there. So yeah, this whole thing of the t naught was probably really dumb, and it didn't really help actually. So we can't take the derivative with respect to time, but we can use the chain rule. We can do d dx of that function, and then dx dt. And sweet. And what we know this, we can just say this is x dot, you know, so just like we did theta dot, just so you know it's a variable that you would have to go back to your problem and see, oh, is it changing, and how much is it changing? Cool. All right, so let's whew, that was brutal. So let's not do that. So let's do y is equal to x squared, and then we're going to differentiate with respect to time. Cool. I don't see time, so we're going to do d dx of x squared, and then dx dt. So this is going to be something we can do. We can do 2x, and then we'll have x, the change in x. So that's how you do it. You know what I mean? You have to get both those things to pop out. So that's going to be very classic when you're using the chain rule. You're going to differentiate this and this like normal, but then you're always going to multiply by that angular speed, that theta dot. Okay, hell yeah. And since I'm not going to go over this video twice, but I guess I am just going to go over it a little slow. Sorry my writing is super tiny on this. But we have a square root, which you can treat as just like something, you know, something in there to the 1/2 power. Or I like to do, anytime where I'm using square roots, or, you know, especially with differentiation, just use decimals up here. You know, make everything in brackets, make it decimals, and then try to get everything to the top. If something is divided, you know, just get it to the top, because it's just so much easier to use the product rule of this times the derivative of that plus that times the derivative of that, instead of using the quotient rule. As long as you get something, if this was downstairs to like the this squared, bring it upstairs to the -2. If it was just downstairs something, you know, bring it upstairs to the -1. You know what I mean? So that's going to be one of the hot tips. because so now just visually I can see this is like, okay, this is something to the 0.5. I'm going to bring down that 0.5, that's where I get this, and then I have to take that something and then drop the power, so it's going to go 0.5 to negative 0.5. Okay, sweet. So, you know, how easy is this? But now we got to take the derivative of inside. This is constant, not going anywhere. Now, this is a constant hooked to something we have to differentiate. It's not a product. If I had a sine theta and then a cosine theta, I would have to use the product rule. And technically, I have a sine theta, so I could use the product rule there, but you don't have to. You can treat this as, you know, some constant times sine theta squared, you know what I mean? And so the constant just you put to the side, you need it, but you can then you can just use that same thing. This is the same thing as like all this to the half power. Just bring down the power 2, and then write whatever in there again, and then take the power down by 1. Cool. And then differentiate what's on the inside. So here we never have to use the product rule. So let's do that. And but I'm gonna write the constants out front right off the bat. In any negative, this is such a hot tip. I'm just gonna say it's parentheses -1. Now again, we're finding the differentiation of this, which is that 0.5, bring it down. All this to the negative 0.5, and then multiplied by the differential of in there. This is constant, so we don't have any adding or subtracting yet. You know what I mean? So and then we're just multiplying by that constant. There it is, -1 e squared, and then we have this sine squared. This is like I swear. I mean, I guess you just get used to it. You got to be like elite status to like enjoy the fact that this, you know, squared or cubed is in between. But once you do, I don't know, it's starting to grow on me. But if you're not to that elite level, I would just honestly write this as sine theta squared, and you're like, oh, okay, I can just use my normal, you know, operations on it. And so to differentiate, we bring down the 2, and then we have everything inside to bring down the power by 1. So we're going to have sine theta, and you could even write a 1 there, you know, just to let yourself know. And then you have to differentiate that inside. And again, this was sine theta squared, and if we take this d theta, okay, hell yeah, we're going to bring down the 2, and then have keep what's on the inside, bring down the power, and then you have to take the differential of the inside. Differential of sine is cosine, and I will go over that every time. So sine graph starts like this and goes like that. Cosine graph starts like this and goes like that. So, and the slope at 0 is always 1. If you type in cosine of 0, you get 1. Cool, hell yeah. And then cosine, the slope at 0 is 0. And so sine of 0 is 0. But this slope is negative. You know what I mean? So we have to have a negative sign. So if you're differentiating cosine, d cosine theta, d theta, that's going to be negative sine theta. But sine, hey, this is a positive 1 slope, so we're saying that's cosine. Okay, hell yeah. So that was the derivative of that inside. So we have bring down the 2, sine theta to the 1. And then derivative of the inside, cosine theta. But we have just completed the d theta part. So that's the only part that we've completed. We want to know d dt, d of this function with respect to time. And we said we could use the chain rule if we did this part, and then take that part and multiply it by this. So just make sure you don't forget to do that, but we do have a double check on reality, so it's just like, oh, I get it. You know what I mean? Double checking your units can make sense why this operator has to be added. And now I'm thinking this is a really good video because I'm a narcissist. No, but yeah, because in part 3 we took that change in y. All right, hell yeah, I ran out of juice. So yeah, in part 3 we took the change in y. We knew our change in angle. We used all that to find the change in time because we knew the change in angle and we knew that angular speed. So we knew theta dot and we knew change in angle, and so so we could get change in time. Anyway, kind of the same process here with the chain rule. So heck yeah, now we're going to multiply it by the angular speed, and for this problem we know it, so we're looking pretty good there. Okay, hell yeah, so we did that. So we took the we differentiated this with respect to theta, and then at the end multiplied by theta dot. And so I'm actually going to take a pause right here and show you how the units work, because if you get all this, you're like, holy hell, like did I make a mistake? And this is why we did part 1, part 2, and part 3, so we can double check our answer. So when we actually plug all this stuff in, these are all constants in our calculator. I'm going to store r. So we have alpha r is 100, alpha e is 60, alpha theta is 60, and so r, e, theta, theta. But then we have this angular speed. Cool, we already found that, 104. So this, you literally can just throw this into your calculator and pop, and plus this though, we gotta finish it off. But you get a number. Alright, so, and you just want to make sure that number has the appropriate units, because I make this error all the time. I'll leave this off, and if I do, you'll see that the units won't match up. So let's go through this piece by piece. So this is going to be meters squared. See that? And E is in meters, or like millimeters. I'm just using generic like meters and seconds. So this is meters squared. So we have meters squared minus meters squared. So this is still meters squared. The negative means that it's 1 divided by meters squared. And this 0.5 means that it's the square root. So this term is just 1 divided by meter. Cool. So that's all that term is. So now moving on to, let's say, let's go to this. Sine and cosine are just percentages of usually something. You know what I mean? And so those are dimensionless. And then E is in meters squared. So cool. So we're going to have 1 divided by meters, and then we got meters squared. So keep those two in mind. That's what we have so far. And then theta dot is in radians per second. Radians are dimensionless, so it's dimensionless divided by second. So we're going to have meters squared divided by meters, so one of these is going to cancel, and we're going to have meters per second. So hell yeah. So that is a good check, and I'm sure my professors told us to do that and told me specifically, but I just didn't have the skills in college to even, I was just surviving. You know what I mean? That's honestly why I'm making these videos, because I'm pretending like I'm teaching myself 20 years ago, and then also trying to, you know, share those tidbits to other people. They're just like, oh, no one's teaching that. No one's pretending like no one knows what the hell's going on, and going kind of back to those basics. And so hell yeah. So now let's do the second one, because again, like what the hell does this even mean? Again, we have this equation for y. If I throw in any angle, if I throw in 60 degrees, I'll get this length and I'll get that length. Cool. Let's change that angle to 61 degrees. Okay, this length and that length changed. Okay, sweet. So if I know the change in y, and then I know, you know, the time it took to change that angle, then I can get the answer. But I don't know the time it took. The time it took to change that angle is a separate thing. That's why we went over that. And that totally explains what the chain rule is doing. You know what I mean? Because we have to, well, I can easily change this angle and then figure out what the y is. Because y, look at this, y is a function of this angle. So yeah, so this, I'm just like reiterating for myself, you know what I mean? Like y, this distance is a function of this angle. So if I change that angle, I change y. But if I want to find velocity, I need this derivative. I need to change y and then divide it by the change in time. All I know is that I can take this and I can find the change in this function with the change in theta using all those rules, but then all I have to do is just multiply by the angular, it's so hard for me to say angular speed, angular velocity, radians per second. And when we do that, we just showed that the units match and kind of, and again, we understand why that's the case. You know what I mean? Because the change in y divided by the change in theta, that doesn't get you very much. I mean, it gets you something. It says, hey, this, you know, if I change this angle a little bit, this thing's going to come down there. I don't know. Maybe you're just like, hey, like this is like the shadow of a building or something, and you're just like, hey, can you change that angle and change that shadow? And you're just like, well, let me make an equation for that, and then specifically dial in your shadow. And then that would be this part of the equation. You would have an equation for, hey, I'm going to change my shadow, and I'm going to change, this shadow length is going to change on this wall because I changed my angle. You know what I mean? So sometimes it's hard to figure out, like, what is the derivative of this? Like, why would that be useful? You would have a change in y given a change in angle. Yeah, it's kind of it can be a nonsensical term where you're just like, that doesn't give me much, but using the chain rule, taking the derivative of this with respect to theta and then multiplying it by d theta dt, hell yeah, we get some velocity. We get the real world stuff that actually, anyway, so we're going to take the derivative of this, same thing, we got to use the chain rule. We can't take the derivative of this with respect to time, there is no t, so we're going to, and this is a constant, we can just put it aside. I like to go over the rules as we do this, and since this video is getting a little bit longer, I mean, obviously you can just do the same thing and see where we got. We're just adding more frosting to the cake. And so, but let's say you don't know this is a constant, you know? So we have two different things. We have e, and then we have cosine theta. I think you could bracket these in and say, hell yeah, we have a product of two things. I'm going to take the derivative with respect to theta. Obviously, we need to take d theta dt. Don't forget about that. But we can just kind of put that aside for now. Taking the derivative of this, I'm going to, if it's a product, I need to do the first times the derivative of the second. Sorry, so I'm going to take e, derivative of cosine. Always draw a cosine graph, you know, something like that. And it's going to be, at 0, it's got to be sine theta, but it's a negative direction, it's negative sign. So I do it like this, -1, just to keep track of the negatives, and then I'm going to go sine theta. Cool. And if we were doing the whole thing, we would put that theta dot right now next to it. But that's going to be the first times the derivative of the second. Now we got to go plus the second cosine theta times the derivative of e. We're still taking the derivative with respect to theta, but guess what? I don't see a theta. So, I mean, this also gets nonsensical. But I could say, hey, what's the derivative of e with respect to e? And then I could do de, and then I'm sorry, no, and then holy hell, d theta. This would be the chain rule on a constant. So I want to take d theta of this. I don't recognize that I have a theta, so let's take de of de and then multiply it by de d theta. And so but again, you're just doing the same thing. I mean, you're just saying, well, de d theta, I don't know what that is either. Yeah, this is probably super nonsensical, but you can't change or the change of a constant, the change of, let's say you had the derivative of the number 2, and then you wanted to, by changing the number 2. Well, if you have a number that is independent all its own and you can't change that property, you can't, number 2 doesn't change, and then so you would have 0 change divided by 0. You'd have a divided by 0, so this is kind of a silly thing, but hell yeah, this constant's not changing, so the top part of the derivative, maybe that's a better way. You know, if I'm actually taking the derivative of e and then changing the angle, yeah, all that aside, I kind of wanted to just make up my own stuff. But what we're doing right here is we're saying e doesn't change. So the change is 0. You know, just like the number 2 fundamentally doesn't change. It's always the number 2. Cool. So E doesn't change, but theta does change. Shoot, you could go from 60 minus 50. You could start at 59 and then go to 60. So that'd be a change in 1 degree. Anyway, that's going to be 0. So let's do this again. First times the derivative of the second plus the second times the derivative of the first. So that's going to be 0. I don't know. I'll try to get better at explaining why the derivative of a constant is 0, but I think to explain even the simplest things in like more complex ways, to be like, oh yeah, I'm not just memorizing that from but I think this is just way easier. It's like a constant doesn't change, but you could change your angle. You know what I mean? There's plenty of things. I could change this angle to like over here. Now the whole disk will come down this way. Now does the radius ever change of the disk? Hell no. Does this eccentricity ever change? No. So I can change the angle as much as I want, but the eccentricity doesn't change. I think, sorry for wasting your time on this. I've been wasting a lot of time trying to come up with little ways to do that. Do like the chain rule on a constant, but obviously you can just say, hey, from this problem, I need to stop stuttering. From this problem, I can change my angle. Cool, but all those constants don't change. So, booyah. And what the hell were we even doing? We were just showing that if you have a constant, you can just set it aside. And the reason is because we have, and if you set the constant aside, you would just take the derivative of cosine. That's going to be -1 sine theta, bring back the constant, and then you would have E. That's the same thing we get here. This goes to 0, and then you get that. So you can do a product rule if you have a constant, multiplied by something you can take the derivative of. Shoot, go do the product rule, get to this part, and don't do that, but obviously say you can't change, the constant's not changing, but you can change the angle. Cool. Hell yeah. Alright, so now we can do this. We're differentiating with respect to theta, but then also multiplying by theta dot. So we have that -1 E sine theta, and then theta dot. Alright, booyah. So that's what we have. The dimensions on this. This is in meters. Eccentricity. Sine theta is dimensionless. Theta dot is radians per second. Radians are dimensionless, so we have 1 divided by second. Meters divided by seconds is meters per second, and this is now dimensionally correct, and we have an equation for velocity. And the cool thing about this, I mean, this I ain't simplifying that anymore. So now I can throw in any angle and pop out a velocity. Knowing my input, we fired this thing up with an electric motor, and this disk is spinning at a constant speed of whatever, and I can know the velocity of this actuator. Sometimes it's just like, what are we trying to find the velocity of? This actuator, up and down, and this equation will give you negatives and positives. It'll be negative this way, and then positive that way, as it's going back and forth. Okay, hell yeah. And then, so all we had to do was just throw in angle of 60, and then all the other parameters, 104.7 radians per second, 60 millimeters for the eccentricity, 100 millimeters for the radius. Now we're going, because our radius is in millimeters, our final answer is going to be in millimeters per second. Divide by 1,000 to get this, and this is the answer in the back of the book. Alright, hell yeah. So without further ado, I'm going to show you that in my calculator. Eccentricity is 60 millimeters. R is 100 millimeters. Theta is 60 degrees. Mode, we're in degrees. And, yep, cool. And then alpha W, omega is angular speed. So I sometimes, put this in my calculator as alpha W. If I have another angular speed, I put it as V. If I have 3 angular speeds per problem, I do U. So W, V, U, if that's something that you want to pick up. But I don't know, be cautious if you overlap and start calling this V. At some point you might want to use this for velocity. So, but definitely W for angular speed. Alright, let's fire this out. And I do like putting in my I'm making way less errors. Anytime I have a negative, just bracket it in and turn it into a foiling process or a multiplication. So yeah, negative 2 becomes negative 1 times 2. So I could do it like that. And even having constants, you know what I mean? Put constants in brackets so then you're not mistaking, you know, you're not forgetting about them. Like this constant right here, because I did simplify this. I have a half here and 2 there. So I kind of just visually knock those out. I still have this negative 1, so I still got to bring that to the front. So we have that negative 1, but we don't have those 2 terms anymore. Hell yeah. And then I don't think I really simplified anything else. Okay, let's do it. So we're going to have negative 1 alpha r squared minus alpha e squared sine alpha theta. We got to square it. And in your calculator, just get used to, like, hey, if you just type sine theta squared, you don't have to. I just remember being a college student just doing all this craziness where it's like you just don't have time to figure out, like, what works and what doesn't work. So I just spent way too much time adding extra parentheses. I would work on your skills of adding less parentheses. You know, it'll help. So all that's bracket, and that's going to be to the negative 0.5. That's like, this whole thing is basically like all that divided by the square root. You know what I mean? That's basically what to the negative 0.5 is. Cool. All right, moving along, we have alpha e squared, and then sine theta, cosine theta. And then we have this omega. And see, angular speed is hard to say. Angular velocity. I don't know why. It's like it doesn't just pop into my head to say angular velocity, angular speed, omega. Sweet. So we have that omega, and then we're going to go add it to a negative 1. See now, yeah, and so if I do have an addition, everything is addition, even if it's an addition to a subtracted element, just by producting in that negative 1. Alpha e, there is no dot above that. I don't know why that dot's there. Anyway, sine theta, and then alpha omega. Okay, hell yeah. And we got it, you know what I mean? So there are some tricks that I'll go over in other videos of like, how do you not make mistakes? Because I make a lot of them, and I think that's why you do part 1. Part 1 is getting an answer that's close to this. I think we got like 7.1 or something, you know, pretty close to that. And so that's in the ballpark, and the actual answer is 7.35. We had a 3% error just by, you know, blowing up the problem or making it life size, and then you know, and then doing that 3-point method. Okay, hell yeah. So to make this not too much longer, I think we're done. So thanks for joining me on part 4. This was differentiation. If I do part 5, you know, we might as well go for it, because this is 16.95 says, hey, find the equation for the angular velocity. We did in terms of theta. And then it also says find the angular, it says find the angular acceleration of A given a constant acceleration. So that was kind of fascinating, because if you have a constant acceleration, then your angular speed will be a function of that acceleration. You know, if you did it as a function of time. Anyway, that's for part 5. I haven't even looked at that. So hopefully you're interested in that. All right, thanks for joining me, and that's the video.